Right. So in this video, I'm going to talk a little bit about the structure of floating point numbers in binary, and sort of explain how the computer sort of calculates this, and it will make sense as to how this works. So, something, just a bit of background knowledge, essentially. So, the standard for 32-bit floats is the IEEE 754 standard. If you don't know who them guys are, I would recommend you look them up. The IEEE, the Institute for Electronics Engineers and Electricians, I think, or something like that along those lines. I can never remember the name fully. Essentially, they come up with all the standards for how things should be stored, how networks should talk to each other, any sort of computing standards. It basically all goes through them, and then they say to companies that make computing systems, this is the standard. Again, a little side note. If you've ever seen your Wi-Fi where it says like 2.4 gigahertz or 5 gigahertz, and I believe another one's coming in now, I can't remember what exactly gigahertz it's running at as of this recording. But they say to manufacturers, this is the standard. You have to do 2.4 gigahertz or 5 gigahertz Wi-Fi connections. Now, obviously, a company can go against them standards and go, I'm going to make something that's 3 gigahertz. But the problem is that might interfere with other things that are happening around the Earth that use 3 gigahertz as a frequency. And obviously, a lot of phones and laptops and stuff might not even use 3 gigahertz because they've not been designed with that in mind. So, a little bit of information on the IEEE, because these are some guys you'll talk about a lot, especially when you go if you're going down a network sort of route, and we'll do a bit of networking on that as well at some point. So a float, obviously, 4.2. This is sort of represented in a lot of different programming languages. So, if you're going to store a float as 4.2 in a computer, it won't actually store it as just 4.2. I'm going to show you exactly how it stores it and how it sort of calculates what the number should be. It obviously uses 4 bytes, which is about 32 bits. Same with a full number. So obviously, if you're using an int, again, it uses 4 bytes, but it doesn't have the same structure. So you have to define that it's a float and define it's an integer, because they use different structures. So an integer will just literally use zeros and ones. A float will use zeros and ones in this sort of way. So this is how it stores a floating point number. Now, it looks scary, but it actually isn't. So the sign is the very first thing. It's the most significant bit because it obviously decides whether it's positive or negative. So the very first bit, which I've highlighted in orange at the bottom, is if it's positive or negative. Pretty straightforward. The exponent is when you times in the number, so the mantissa or significand, by times 2 times 10 to the times 2 to the whatever. So say times 2 to the power of 7. The exponent will come up as 7. Now, I'll explain a little bit more about this later, because there is a little bit more to it than that. And then the significant or mantissa is just the number itself. So this is a floating point number. So this is 5.2 in particular. What this number stores is the number 5 and then the number 0.2, and I'll show you why it's got all these zeros and ones in it for 32-bit at least anyway. And obviously right at the end is the least significant bit, so the very last thing is the least significant bit. It basically means that it doesn't matter what it's really on, depending on how long the number is. It's not going to make that much difference in the calculations, but obviously if you're working for somewhere like NASA, things like that would make a difference, and there have to be means and ways around that, but you don't need to know that for now. So basically what it does is it takes this number that it stores, so these 3 sections, which it just stores as one big number at the bottom here, and it uses them like this. So the green part is the 5.2. The sign obviously is just if it's positive or negative, so either 0 or 1. And then the exponent is the power of the times 2 section, so 2 to the power of what that is. That is 5.2 in a computer. So it basically takes this number here, so the sign, the exponent, and then the mantissa. Well, specifically for 32-bit systems anyway, and puts the mantissa here, the sign there, and the next one up there, and uses this calculation to work out what the number is originally. And I'm going to go over what that is in a separate video, but this is essentially what the structure is going to be. So the structure is, in a computer, it stores it like this along the bottom, and then it uses this calculation, so it basically rearranges these three things here to do that, and then it works out what the original number was based off that. So stores it like this, uses that calculation to get you back the original number. So storage is different to what it actually prints out on screen. That's something that we're going to use for that, and I'm going to show you in the next video how to calculate the mantissa, calculate the exponent. Obviously the sign is just, if it's a positive number, you just leave it as 0. If it's negative, you put it as 1. I don't need to go over that. But I'll show you how to calculate these two, and it should hopefully make sense. Be ready for it. It's going to be a bit of a killer of a video, but I'll try and go through it as best I can. And again, if you've got any issues, come and see me, come and ask questions like you can. That's what I'm here for. And hopefully we'll be able to do it as well in lesson time at some point.